And so he works in the areas of option pricing and stochastic optimal control. His research interests, of course, in statistics and sports. And he'll talk to us today on probabilistic excitement in sports games.
Good. Thank you for the introduction, and an exciting conference in general, in fact. Just one little correction. I'm in the Department of Statistics rather than Biostatistics. Good. Sure. So today, is there a pointer? Oh, that one. Okay, good. All right, so I'm going to talk about a concept which many of you probably sort of feel in terms of if you see a game, how exciting it is or how boring it is. And I'm just going to sort of put quantitative measurement of these concepts. I should mention that this is a joint work with two students in our department, Tomoki Ichiba and Mladen Laudanovic. And some of my work in all directions, including sports statistics, is on my webpage. As I mentioned that I'm going to introduce a quantitative measure of the excitement of sports games, and this measure can be thought of as a variability of the expectancy of winning as a game progresses. And I'll specifically demonstrate this concept on soccer games, not because there is anything special about soccer, but because the data on soccer events are sort of most reliable in this direction. And also that there is another reason why that you can compute the theoretical model win expectancy for soccer games from a simple Poisson model. And there are certain things which you would imagine that if you have such a model, it is more exciting to see a game with two equal opponents rather than having one-sided game. And if you have a particular team, the more exciting games would be played against a slightly stronger team. And I'll show you that I actually have data from FIFA World Cup 2006 game where the winning expectancy was independently estimated by betting markets, and thus there were two possible ways to compute the expected and realized excitement, one from the model and one from the data which we saw in trading. So what is the motivation of excitement? So you might think that high excitement of a game comes with certain factors. One factor is that there are more changes in the score lead. So the more fluctuations you see in this direction, then you would say, okay, that's probably more exciting than one-sided game. If you see a change which is more dramatic, that's also something which contributes to an excitement of a game. And the later in the game you see a decisive moment, that's also more exciting if you compare it to an early decisive moment. So this is pretty much a motivation which I'm going to talk about. Of course, you can think about other measures of excitement. There could be some kind of, if you see a spectacular shot, or if you see certain athletic performance. But you know, these are excitements which I cannot quantitatively capture. So that's why I talk about probabilistic excitement. So the probabilistic excitement is essentially related to these 3 points. And once you have these criteria in mind, one possible statistics which does exactly what is mentioned here is some kind of weighted average of changes in lead in some sense, meaning that you put more weight to the later events than in earlier events. And this weighting is, if you want to do it like properly, this could be done through changes of probability of winning. So probability of winning is or win expectancy is the key statistics which in turn will define the excitement. If you think about it, the more changes to the expectancy, the less predictable is the outcome of the game. Okay, so let's go into some mathematics. The formula looks really horrible, but nevertheless, the explanation is very simple. So one thing is that I'm proposing that excitement should be, in some sense, some variability of the winning expectancy, and this variability can be measured by the total variation of the winning winning expectancy. What is the total variation? Total variation is essentially the length of the arc length of the graph of a given function f. It's a vertical component of that. And this is like how you can formally define it mathematically. So essentially these are like, fluctuations of this probability. And the longer is the path of winning expectancy for a given team, the more swings there are in the game, and thus the game is more exciting according to these motivational points. Now, so formally you can define that the excitement is the total variation of the probability of team 1 wins plus total variation of probability of team 2 wins. In fact, these two should be equal because probability of one team winning is 1 minus probability of the other team losing, but just for the sake of symmetry, I put it here. It's useful because when I use trading data, the trading data don't necessarily possess this symmetry. So, this is a way how to kind of smooth things out. I can give you a few. I should mention one point probably. According to this definition, a game which you have seen has zero excitement because you know the outcome. So once you know the outcome, you know for sure that one team or the other team is going to win. So essentially, before watching the game of which outcome you know that a certain team is going to win with probability 1 and the other is going to lose with probability 1, and thus the probability doesn't change during the game because it's a done deal. So in this respect, you can also, like a same game can have different excitements depending if you have a full information or if you don't have full information. So this is so zero exciting game is something which you know upfront. So you can the minimal level is 0. There are some games, although US is not really in favor of draw as an outcome, like US type games. So, but nevertheless, for soccer, I have to include this outcome of probability of draw. So, if draw is possible, I work with a modified version of that, which is the sum of the total variations of these three probabilities. By the way, this concept has, since I'm working in quantitative finance, this is a clear financial interpretation in terms of betting markets. This is if you had a limited resource, if you had like $1, and if you knew exactly when the goals or when the swings in the game will happen, then the total variation is the maximum profit you can get out from this information. So if you had like, say $100, and if you knew, okay, there will be a goal in 15th minute, and there will be a goal like in 66, and if you correctly buy and sell these contracts, this is the maximum amount of money you can possibly make. Okay, so that's the analogy to finance. In general, the total variation of winning expectancy is mostly changed if there is a game-deciding event close to the end of the game, or if there are a number of events where the game lead is changed, or another thing is that you have a weaker team which unexpectedly wins or draws the game. So these are factors which contribute to increased excitement. And on the other hand, you would expect only small changes in the total variation of winning probabilities if the game is one-sided with an early lead from the favorite team. So that is essentially already a consequence of the definition. As I mentioned, our approach to measure the excitement by variability of the win expectancy can be applied to all sports which are played with two competing teams. But not only that, you can think about it like if you have like Formula 1 or some racing competitions, then also each of the individual competitors has probability of winning that event. So you can also actually include such situation in this model. And the trouble here is how to compute win expectancy. That's essentially the question which we ultimately face, because in order to compute the excitement, you need to know what's the win expectancy. And the win expectancy can be essentially computed from either some model, I use the model, but it should be some model, or you can, these days, you can observe it from the betting market, which gives you an independent estimate of these win expectancies. But both approaches have their drawbacks, because no matter how complex model you have for no matter what kind of game, you will always sort of miss some little nuances of the evolutions of the game. And on the other hand, betting market might overreact in situations when there is no change in win expectancy in some sense, just because there are some speculators who just enter. So neither of the two approaches is perfect. Now, as I mentioned, the problem with computing win expectancy from a model is sport dependent. And unfortunately, I know that from observing betting market, that people have done their homeworks for pretty much for every sport. So there are certain, I would say, financial groups which did computed essentially probabilities depending on what is going on the field, what is the winning expectancy of each team, but for a person like say who is not really making living out of it like me, is developing these models could be very complex for complex sports, such as say American football. American football has a relatively non-trivial way how to compute win expectancy. Why is the problem? Because some of the games, including American football, have a strong memory. So meaning that essentially these systems don't forget what's going on or what happened so far, and thus the model actually can go and sort of fork. So in a way, it really it is hard to capture all these details. So the simplest analytical tractable models assume that there is no memory. So meaning that the current score is the only indicator of the winning expectancy of what's going on. And these models with no memory are called Markov models. And there are not that many sports, but there are some sports whose evolution could be approximated well by, I'm saying approximated because there is never perfect fit, but reasonably well sports which possess this property would be baseball, tennis, soccer, or hockey. You know, that's and I'm saying reasonably because there are things which, you know, again, you have memories in these systems, although I would say like weak ones. And there you see my natural choice. The thing is that baseball has, you know, people who work in baseball statistics, they probably would agree with me that, you know, this is probably the best game in terms of computing winning expectancies because people have done it, and they essentially, you know, they've done numerous studies to quote, you know, what's the, given the score, given the state of the system, what is the probability of a team winning. But the problem is for baseball, it's very hard to check it with betting, with data from betting markets. Why? Because the data from betting markets are quoted according to time ticker, not according to the score. So, you know, putting these two in perspective is next to impossible. I mean, unless you really mark every event and say, okay, this happened, you know, this home run happened exactly at like 1751, and you go into these trading data and see, okay, 1751, there is some jump there. So it's a little bit difficult to do it. Tennis is also nicely tractable. Again, the same problem is that this is played in sort of discrete, these are sort of discrete time market chains, so there is no need to mark when the event happened in terms of time, so it's also difficult. So a natural candidate to illustrate this concept is essentially soccer or hockey, and soccer is sort of very popular, at least in European terms or European market, and so I actually have significant data from trading which could be put into perspective with what's going on the field. Okay, betting market. So the betting market now is organized these days as a financial exchange, meaning that traditionally, giving you some feedback, traditionally people went to a bookmaker, and the bookmaker was the partner who matched certain odds. But the bookmaker was matching odds like for the event and against the event for different entities, and the bookmaker essentially was charging a certain overhead for doing this. And with internet and with all these electronic markets, there is a huge change, because what happened is that you can trade as an individual or as a financial entity. You can buy and sell these contracts. So you can not only bet for the event, but also against it, effectively killing any overhead which used to exist. So now you effectively can get a fair price on the market, meaning that if you buy all the outcomes, you would probably, with a payoff, if you had a pay of 100, you would probably pay 100.20 cents. So the overhead is in scale of 0.2%. Okay, so it's very small. So they are now organized as major financial exchanges such as Betfair.com. That's very efficient, reliable in estimating the correct expectancy at any given point during the game. For example, Betfair.com, if you have like in soccer, a typical game in English Premiership attracts around 15 million euro, which means it's a sizable financial contract. U.S. entities, I should mention, before, that I'm not doing any propaganda here. U.S. entities cannot participate in the market for legal reasons, but nevertheless, that doesn't stop the betting exchange to trade U.S. sports events as well, which are traded by foreign entities. Now, so as I mentioned earlier, soccer is the focus of the talk, since it's both tractable from the model and there is enough data from the betting market to check it. Now, I suppose that most people know that, but nevertheless, those who don't, there is something which is called Poisson model or Poisson process, And Poisson process is essentially a memoryless counting process, meaning taking integer values in continuous time. And its evolution is given by, it either stays at the same level with this probability within the interval t and t plus delta t, or it jumps by 1 with this probability lambda times delta t. So I usually, when I teach this thing, or mention it in terms of sports, you can think about it as a bathroom break. If you watch like a hockey game, expect 3 games per the whole game, 60 minutes. If you leave for 1 minute, the probability that you miss a goal is 1 in 20, roughly. Okay? Because delta t is 1 over 60, and you expect 3 goals, so 3 divided by 60 is 1 in 20. So that's essentially gives you the idea how the process is constructed. Now, it's particularly suited well for evolution of scores in soccer or to some extent to hockey, because these games, you can argue that they don't have strong memories. Given the 2 equations which I've shown you before, you can compute what are the exact probabilities of these events. So that probability you see k more goals is equal to this, and k more goals for the other team you see is that. So this is like a standard Poisson distribution. So I'm denoting xt, yt is the current score at time t in the game, and then you're marking the end of the game. So essentially the result of the... Now, the parameters lambda and mu, they are, I call them scoring intensities of the 2 teams, and they are related to the expected score by the following relationship. So you see the number of expected goals from now to the end is multiplied by its lambda, so that's multiplied by how long time is left in the game. So these are like, that's the number of goals you should see on average. One thing which is interesting is the memoryless property implies that the time between the goals is exponentially distributed with parameters lambda and mu. And in this model, you can write down the formulas, explicit formulas for the win expectancy each team, and for the expectancy of a draw. And once you do it, you get some, formulas like that, which looks horrible, but you can easily put them into some computer spreadsheet and have them ready. So some examples of games. So evolution, I'll show you the evolution of probabilities which are implied by the Poisson model of scoring of 3 events: draw, win of Holland, win of Argentina during the Holland-Argentina game in the FIFA 2006 World Cup. The game ended with, well, one thing is that scoring intensity for Holland was estimated as 1.05 and for Argentina 1.57. So there is one thing which I didn't mention both in this talk and in my papers, is that from numbers which you see on the market, the market implies you certain intensities or certain expected goals you would see. So these are, once you see the prices tell you, okay, the market expects there will be 1.05 goals from Holland and 1.57 goals for Argentina. So these are implied parameters. Now, before I turn the page, the question is, what is the most boring game? Okay, given this, what? No. In this intensity, what would qualify as the most boring game between these 2 teams? No. I mean a score, or evolution of it. I'm asking for an evolution. How you got there. What? Argentina was now blind goals early. Okay, well, yeah, that's a good point. So, I mean, that's a good direction. So the most boring game is a goal from Argentina in the first minute, which doesn't, and Holland never scores. That would be the most boring game, because the in the start of this game, it's not the other competing guess is actually 0-0. Okay, so I mean 0-0 could be also the most boring game, but in the setup, if you look at these intensities, the most valuable contract, which out of the draw, win of Argentina and win of Holland, is win of Argentina. So if Argentina converts the goal right away, the win will start to walk towards 1, and the added probability would be the smallest. So in fact 0-0 is not as boring as 1-0 from Argentina from the early lead.
Why isn't 10-0 even work?
What?
10-0 would be work.
Well, you see, if you add once you lead 1-0, if you see a second goal, it doesn't change the variation. You see, because the win of the team is already walking towards 1, it's converging to 1, and if you add a goal, it would just be converging faster, but it would go in the same direction. You see, so in this, as it is defined, 1-0 and 10-0 would be equally, exciting. Well, but there are different statistics which you can think about. There is some probability that, things can go wrong, like some, so of course, probability that you would see some surprises is greater for 1-0 than for 10-0. So, I mean, and that's how it looks like. So if you start with probability of draw, since there is no goal, okay, it goes and starts at some, 25% or whatever, and it converges to 1. And these are probabilities that Holland wins and Argentina wins. So as you see, the probability that Argentina wins is almost 50% in that expected. If there was an early goal, it would go like that. A second example is something which would qualify as a boring game, or at least upfront boring game. Togo, France. Okay, so France, reigning champion at the time, I think. Togo is like a weak team. So France scored relatively late in the game, in the 55th and 61st minute, which is relatively late for what it is. And you see the market estimates 0.37 goals for Togo, 2.65 for France. The expected excitement is 1.28, the lowest for all the games played in the championship. So, and here are the, so the draw goes, there is always one event which converges to 1, because one of these things will happen. And you see that there is like a kill which gets it to 0 after the first and second goal. Togo win is not very likely, and France win of France goes like that. And this illustrates the concept that the game would be equally exciting if you had 1-0 or 2-0, because if you had just 1-0, you wouldn't see this jump. But the jump is already in the direction which you would expect to go. So essentially, there is no more first variation added there. Ghana, USA is my last example. Two relatively equal teams, 1.37, 1.16. The expected excitement is 2.55. That was the highest among all the games in the championship. And the game ended up 2-1 for Ghana, and you see that that's how that there was something interesting about it. So first goal by Ghana, then equalizer from the US, and goal for Ghana. So that's how it went. Ghana wins, the evolution of that, and the US wins. And you see that the later in the game there would be like a decisive goal, the larger would be this drop. And Okay, I finished just with some tables where I illustrate the concept that you can, I took elimination round games excited ordered by the excitement level. So draw was possible, and you see the most exciting, there are certain things which, this is the parameters which are implied from the market. That's how the market sees them. This is the actual score. These are individual contributions from variations from win, loss, and draw. This is the total realized, and this is from Poisson model. So these are data which we got from the trading. And this is what we got from the model, and this is what you would expect before the game started. So the excitement, you can actually split it, because before the game starts, you have a certain prior idea about how the excitement would be. Like, you know, Holland, Argentina would be more exciting game than Togo, France, in some sense. But, you know, the realized game might end up very different. So, as you see, there is a good match with the model and with the total, with the exception of few things. Portugal, Holland, okay? The realized excitement was higher than the from the model. Why? There were 4 red cards given in the match. Okay, which is something the model doesn't capture. You know, the model depends only on the changes of goals. So essentially, a red card effect is captured by the trading, not by the model. And there's one thing which is England, Ecuador is the trading has smaller variation than the model, because the traders believe that England had the game under control anyway. So you see that the most exciting games have like sort of 1-3 or 1. This is exciting because that was the game which happened in 94th minute or something. And the least exciting games are one-sided. 3-0, 2-0, 3-0. That's something about it. We did something from, you know, because that was elimination round, we could actually take a similar data from the trading. And the last thing which I want to show you, that's the graph of the expected excitement as a function of intensity of scoring. So, and you see that it actually increases around this diagonal. So if you have 2 equal teams, the more scoring you see, the more exciting game you would have. So for instance, in a way, if you compare like soccer and hockey, which has a higher scoring intensities, hockey would have more swings in the game as compared to soccer. Last thing I want to mention, you can have an exciting game even if one of the teams has zero ability to score. Why? Because they can still manage to get a draw 0-0. Okay? And there is like so it could be exciting. And I think this would conclude my talk today. So thank you for your attention.